Hey everyone, I wanted to share with you something new that I've been trying out at Black Rock Forest. And let me start by showing you a picture. This is the woods behind our house on Taylor Road, which is not far from Black Rock Forest. There I am, and what I have set up in the middle of the woods here is this little tiny LIDAR projector, scanner, which I bought. We have a wildlife camera that's in the back, takes pictures of things like coyotes and foxes and deer and so forth. Will happen to catch me. And as you can see, it's kind of like Black Rock Forest. Of course, there's some colonial fence back there, but there are lots of trees. It's winter, so there's no foliage. And what I've always wanted to do is to understand more about the community that surrounds a plant or the organisms that are found inside a forest that differs in biodiversity. Well, the Black Rock Forest experiment with the oak removals created lots of different plots with different levels of diversity by removing oaks or not removing oaks. You're familiar with the experiment. And so I decided to think more about what we could measure there. It's a bit difficult because when you measure the impact of deer, we have one exposure inside of the plot. If you measure the temperature, we have a couple of temperature recorders and a couple of soil moisture recorders that Sarah Bruner has put in place, but that's not a lot to measure a whole plot in terms of what a plant on the ground is experiencing and what an organism is experiencing. And the replication is so low that it's really quite a challenge to statistically analyze the data. We have just 2 points within a plot, which is only a few replicates for each treatment. And as you know, we've been flying the drones above, and that's sort of fun until we lost a couple of drones, but the difficulty there is that we don't really see what's going on the ground. And then when we're on the ground, the difficulty there is it's hard to measure in great detail many of the things that might be of interest. One of the things we have been doing that Sarah has done and others was to take whole canopy images using a fisheye lens. And that's pretty interesting to me, but it tends to reduce it down to just sort of the light environment based on the what the plant might see at that particular point where the camera is held. And that's sort of interesting because you could do a bunch of them per plot, and I like that. But I still was really interested in more information, and the structure is missing from that kind of analysis. We use structure for motion, but structure for motion is not very good for scanning around your environment. It is good for scanning within your environment, so we can put an object in the center and go around it and scan it, or we can fly over it and scan it, but you can't stand in the middle of the plot as if you were a plant and turn around and take photos. It can't stitch those kinds of images together. What I really wanted was something like ground-based LIDAR, as far as I could tell, but I've never used LIDAR before. I've only seen it in talks and read about it, and of course our good friends in Idaho have done some pretty amazing work with it, and I thought if only we could do it here at Black Rock Forest. Well, I was looking for a LIDAR scanner to put on a drone, wondering if the technology has got to the point where it's small enough, and it is, but you need bigger drones, and they fly a short amount of time, and the resolution is pretty low, and probably the drone will crash again, so I wasn't all that enthusiastic about it. But while looking for that, I came across this very, very small scanner, which is produced by Leica. And as you can see, it's called the Leica BLK360. There's the unit sitting on top of its tripod. And there's the propaganda, simple, powerful, and we have these cool guys who look like they're from Brooklyn telling you how it works. It is primarily used for construction and architecture. It's really an indoor instrument. You put it inside and it'll scan the room and it'll measure all of the detail about where the lights are and where the walls are and where the furniture is and so forth. And it's used quite extensively by the industry for that purpose. It's not really an outdoor instrument. On the other hand, I saw this picture in some of their propaganda, and it can be taken outside. Here they're doing architect of a ruin that's out there, but hopefully the sheep aren't there, because of course these sheep, if they're wandering around, will make a mess of the LIDAR scan. You don't want anything moving in there. But I thought it can go outside, and I spoke to the salespeople and said, yes, it can go outside if it's nice weather. And I thought, well, I don't like going outside unless the weather is nice myself. So, you can't really scan if it's raining anyway. I suppose it doesn't work in the terrible cold, but there it is, and it's such a small unit. And another cool guy from Brooklyn. And so, I thought, you see how tiny it is? I assume his hands are normal size, but let's go and take a look at the actual thing. Here it is. This is not a picture of mine, but it looks exactly like that. There's the unit, there's the iPad you need to control it, and then there's the case that goes on top of it, and it sits on a tripod. And by comparison, here the behemoths are super expensive, $30,000, $40,000, $50,000 for these things. And then here's this little thing, which costs about $15,000 if you buy a demo, about $18,000, if you buy it brand new out of the box. So I bought one. I talked to the salespeople and asked if I could buy their demo unit, and they sold it to me, and they gave me an education discount on the software. And I thought, let's run with it. It's always fun to try something new. It was the winter break, and before we get into the mess of faculty reviews and job candidate searches and budgets and finding a new chair and all that horrible stuff, I thought, let me have one more chance to play. And I went out with this unit in the back of my home and did my first LIDAR scouting with this little unit. I will tell you that the learning curve is steep for this stuff. Simple, powerful, it's just a joke. But even it is tiny. The unit doesn't weigh more than maybe a pound or two. It runs on batteries. It fits in a small little pack, and you can take it anywhere. And I wanted to show you what the first scan looks like from exactly where I was standing. I was standing behind a tree. This is below the scanner, and you can see that, of course, it can't see what's underneath it, but the resolution is not too bad. Of course, it depends on the reflectivity of the substance, whether it absorbs the laser, whether it reflects it in the angle, and so forth, all of that stuff. But if we zoom out, there's those sort of fascinating, mesmerizing pictures of the forest, and this is immensely appealing to me because it has all of the 3D structure. And if I were a plant in the center, this is the neighborhood that I would see. And as you know, there are lots of statistics and things you can calculate once you have these kind of data. That is the part which is incredibly difficult, at least for someone who's spent a couple days on it. Maybe if I took a class for a few weeks or spent a few years doing this, I'd get better at it. But pretty impressed at the quality of the output of this tiny little device. You've seen the back. That's my home in the back. That's the top floor. There's the deck in the back, and so forth. So it can actually see pretty far, but of course that's a very reflective surface, the house, and eventually it all diminishes. And if we look up into the sky, of course, the sky doesn't have any return data. So what this software does, and it's called 3D Forest, I looked around and there's lots of software that's all highly unstable or super expensive, or it runs on Java, or it runs on Python, and I tried to learn Python and Java quickly, but it was hopeless because school was about to start, and in fact it started yesterday. But I really wanted to do something that would make me feel like I was doing something that was related to research and not to administration, and something new. So there you go. What this software does, 3D Forest, and it's open source, which means there's not a lot of help for learning how to use it, and I can't tell you how many times this thing has crashed on me. First thing it does is it separates the vegetation from what it's called the terrain, and that's important for a lot of the statistics it will calculate later. But then what I was really interested in was, and let's change the color to something a little bit more pleasant. How about this green? So we can see the ground, and then there's the forest. But what I'm going to do now is I'm going to turn on all of the point clouds, and it actually tries to identify trees. And once it identifies trees, you can then do statistics on it. However, LIDAR data is actually quite difficult to use because objects that are behind objects are not seen or fragmented. And then when you get to really fine divisions like little twigs and whatnot, it has a really hard time trying to track what twig belongs to what tree, just like the human eye. And there's some really super cool software that gets around some of that problem. But this is what I've been able to do so far. And I have to say, I'm totally jazzed by this. I'm going to turn off the vegetation scans. And you'll note that when I do that, there's a lot of data that actually hasn't been used. So I'll go down and turn off. What I'm doing now is turning off the vegetation scans so I can focus on the tree scans, which are now separate point clouds. So each of these trees is its own point cloud. And let's see, I think there's still some vegetation turned on someplace. There, okay, turn it off. Ta-da! There are the trees. Isn't that amazing? I mean, you know, they're not different species. Wouldn't it be cool if we could actually tell what the species are? But it is identifying these as individual point clouds. And when you have those individual point clouds, you can then do things like measure diameter at breast height. You can convert it to voxels and measure volume. You can do all sorts of cool stuff. There are no leaves on the tree, so we don't have any sort of canopy images. There's that tree, which is behind another tree, so of course it doesn't actually produce something that's terribly useful, but it is, in terms of what the plant is seeing that tree behind the other tree. So, you know, let's scoot down. There is the hole from which I think of it as a hole in which the scanner was placed. And then when we go down through it, get down to the bottom here, right, and then turn it around, you can see that we now have the forest all around us, right? And that's pretty cool. So here we are, standing on the ground, and now we can sort of turn around, reduce the forest a bit. And you can also see when I do this that it's definitely just a bunch of points. Each of these trees is its own separate point cloud now, and there are the trees. And this is what a plant is seeing if it's sitting in the center. This is what surrounds it, and you know, you can walk through it and so forth. But it's pretty mesmerizing. So what I would like to do is, if this can turn into something useful, other than produce pretty pictures and entertain me in my time off, is to go to the oak removal plots and do maybe 4 or 5 of these scans per plot and get some sort of average measure of the structure from the standpoint of a plant, and to, you know, associate that as well with the whole canopy imaging. And then some of the measurements, like the water and the soil moisture, the temperature and soil moisture that Sarah Bruner is doing, and sort of coordinate it with lots of other things, and see if we can come up with some really interesting changes that have occurred when the oak trees or the non-oak trees were removed. Okay, that's it, folks. Thanks for listening, and I'll see you all soon.